Welcome back to the Interview Prep Podcast. Today we're tackling one of the most common and most important questions you'll face in any GenAI interview. When should you fine-tune a model? When should you use prompt engineering? And when should you reach for RAG? These three approaches are the fundamental toolkit for customizing LLM behavior, and knowing when to use each one is what separates a junior engineer from senior one. Let's start by defining each approach clearly. Prompt engineering is the art and science of crafting inputs to get the desired output from a pre-trained model. You're not changing the model at all. You're just getting better at talking to it. This includes techniques like few-shot examples, chain-of-thought prompting, system messages, and structured output formats. Fine-tuning means actually modifying the model's weights by training it on additional data specific to your task. You take a pre-trained foundation model and continue training it on your domain-specific dataset. The model literally learns new patterns and behaviors. Modern approaches include full fine-tuning, LoRA, QLoRA, and adapter methods. RAG, or retrieval augmented generation, is a hybrid approach where you keep the model unchanged but augment its input with relevant information retrieved from an external knowledge base at query time. The model gets context it needs to answer accurately without having to memorize everything in its weights. Now, let's talk requirements. When an interviewer asks you to choose between these three, you need to ask clarifying questions first. How much domain-specific data do you have? What's your latency budget? How often does the underlying knowledge change? What's your compute budget for both training and inference? Do you need the model to follow a specific output format or style? And critically, what's your accuracy requirement versus cost trade-off? Let's go through the architecture of when to use each approach. Use prompt engineering when you need quick iteration with no training cost. It's your first line of attack and should always be tried before anything else. Prompt engineering excels when the task is within the model's existing capabilities. You just need to steer it. For example, if you want GPT-4 to write SQL queries, you don't need to fine-tune it. A well-crafted system prompt with a few examples of your schema and query style will get you 90% of the way there. The key techniques here are system prompts for persona and behavior, few-shot examples for format and style, chain of thought for reasoning tasks, and output schemas using JSON mode or function calling. The limitations of prompt engineering are real, though. You're constrained by the context window. Every example you include eats into your available tokens. The model can't learn genuinely new knowledge through prompts alone. And complex multi-step instructions can be fragile, with the model sometimes ignoring parts of long prompts. Now, when should you fine-tune? Fine-tuning is the right choice when you need the model to consistently follow a very specific output format or style, when you have a well-defined task with hundreds or thousands of high-quality examples, when you need to reduce latency by removing the need for long prompts, or when you need to teach the model domain-specific knowledge that it genuinely lacks. Let me give you concrete examples. If you're building a medical coding system that needs to output ICD-10 codes in a very specific format, fine-tuning on thousands of examples will be more reliable than any prompt. If you need a model to consistently write in your company's brand voice across thousands of customer interactions, fine-tuning captures that style more reliably than a system prompt. If you're deploying on edge devices and need a smaller model to perform a specific task well, fine-tuning a 7 billion parameter model can match a much larger model for that narrow task. Let's dive into fine-tuning methods. Full fine-tuning updates all model weights and requires significant compute. You need high-end GPUs, often multiple A100S or H100S, and the full model in memory. This gives the best results, but is expensive and risks catastrophic forgetting, where the model loses general capabilities while learning your specific task. LoRA, or low-rank adaptation, is the current industry standard for efficient fine-tuning. Instead of updating all weights, LoRA adds small trainable matrices to the attention layers. This reduces trainable parameters by 99% while achieving comparable performance. QLoRA goes further by quantizing the base model to 4 bits, allowing fine-tuning on a single consumer GPU. These are the methods you should be talking about in interviews. The training pipeline for fine-tuning involves dataset preparation, which is often the hardest part. You need high-quality input-output pairs. Data quality matters far more than quantity. 1,000 carefully curated examples will outperform 10,000 noisy ones. Use techniques like data augmentation, synthetic data generation from stronger models, and careful deduplication. Monitor for data leakage between your training and evaluation sets. Now let's get into RAG, which is arguably the most practically important of the three for production systems. RAG is the right choice when your knowledge base changes frequently, when you need citations and source attribution, when you need to ground the model's responses in factual data, and when you want to avoid the cost and complexity of fine-tuning. The RAG architecture has several components. First, the ingestion pipeline. You take your documents, chunk them into manageable pieces, generate embeddings using a model like OpenAI's text, embedding 3 or open source alternatives like BGE or E5, and store them in a vector database like Pinecone, Weaviate, Quadrant, or Vector. Second, the retrieval pipeline. When a query comes in, you embed it using the same embedding model, perform similarity search against your vector store to find the most relevant chunks, and optionally re-rank the results using a cross-encoder model for better precision. Popular re-rankers include Cohere re-rank and open-source models like BG re-ranker. Third, the generation step. You construct a prompt that includes the retrieved context along with the user's question, and the LLM generates an answer grounded in that context. The prompt template matters a lot here. You want to instruct the model to only use the provided context and to say when it doesn't know. Advanced RAG techniques are what really impress interviewers. Hybrid search combines dense vector search with sparse keyword search like BM25, giving you the best of both worlds. Query decomposition breaks complex questions into simpler subqueries. HyDE, or hypothetical document embeddings, generates a hypothetical answer first and uses that to search, which can improve retrieval for abstract queries. Contextual chunking uses the surrounding context when creating chunks, not just arbitrary token splits. An agentic RAG uses an agent loop to iteratively refine search queries based on initial results. Now here's the key framework for your interview. Think of these three approaches as a hierarchy. Start with prompt engineering. It's free, fast, and often sufficient. If prompt engineering hits its limits, consider whether you need the model to know more or do more. If it needs to know more, use RAG. If it needs to do more in a specific way or style, use fine-tuning. But here's the advanced insight. These approaches are not mutually exclusive. In production, the best systems often combine all three. You might fine-tune a model to follow your output format perfectly, use RAG to ground its responses in current data, and use prompt engineering to handle edge cases and adjust behavior without retraining. Let's talk about evaluation, which is critical for all three approaches. For prompt engineering, A/B test different prompts with a held-out evaluation set. Track metrics like accuracy, format compliance, and latency. For fine-tuning, use standard ML evaluation, train test splits, loss curves, and task-specific metrics. Watch for overfitting, especially with small datasets. For RAG, evaluate both retrieval quality using metrics like recall at K, mean reciprocal rank, and NDCG, and generation quality using metrics like faithfulness, relevance, and answer correctness. Tools like RAGAs, Deep Eval, and custom LLM judge evaluations are standard. Let's cover some advanced topics. First, when does fine-tuning actually hurt? If your training data is low quality, biased, or doesn't represent production traffic, fine-tuning can make the model worse than the base model. This is especially true for safety. A fine-tuned model might lose safety guardrails present in the base model. Always evaluate safety alongside task performance. Second, the cost analysis. Prompt engineering costs nothing upfront, but may require longer prompts and thus higher per-request costs. Fine-tuning has upfront training cost, but can reduce per-request cost by enabling shorter prompts and smaller models. RAG has infrastructure costs for the vector store and embedding pipeline, but avoids retraining costs when knowledge changes. Third, latency considerations. Prompt engineering with long context adds latency from processing more tokens. Fine-tuning can reduce latency by removing the need for lengthy instructions. RAG adds retrieval latency, typically 50 to 200 milliseconds for the vector search and re-ranking step, but reduces generation latency by providing focused context. Here's your whiteboard summary. Draw 3 columns: prompt engineering, fine-tuning, and RAG. Under each, list when to use, key techniques, pros, cons, and cost profile. Then draw arrows between them showing how they combine. Show a decision flowchart. Does the model need new knowledge? If yes, go to RAG. Does the model need a new behavior or style? If yes, go to fine-tuning. Can you describe what you want in natural language? If yes, start with prompt engineering. Now let's wrap up with key interview phrases. Say prompt engineering should always be the first approach, as it provides the fastest iteration cycle with zero training cost. Use fine-tuning is appropriate when you need consistent behavioral changes that can be demonstrated through examples, not instructions. Mention RAG provides dynamic knowledge grounding without retraining, making it ideal for frequently changing information. Talk about LoRA and QLoRA have democratized fine-tuning, reducing compute requirements by orders of magnitude. Say the best production systems combine all three approaches: fine-tuning for base behavior, RAG for knowledge grounding, and prompt engineering for runtime flexibility. And emphasize evaluation methodology differs across approaches, with RAG requiring both retrieval metrics and generation quality metrics. That's episode 3. These 3 techniques are your bread and butter as a GenAI engineer. Know when to use each, know the trade-offs, and know how they combine. Next time, we're going deep on designing a real-time ML serving pipeline. See you then.